Hello, everyone. Today, this evening, I'm going to give you a short and ongoing project about what I'm doing. And actually, it all starts about supercapacitors. And as some of you may know or may not know, what is supercapacitors is literally like a conventional capacitors, but it can actually store charge much more than a capacitor. And compared with the batteries, it can actually give much higher power, which means the energy per unit time you can extract from the device is much more than the batteries. And it's actually been demonstrated in some trams in the South China where you can actually charge it in one stop, and then it's actually the energy is being used by the trams to move on to the next stop, and it's being charged again. And in some of the radio frequency transmitters, it's being used to actually transmit the signals over a long distance. And this maybe in the future you see it's being used for powering more like small but flexible devices, maybe on your hand. And one of the typical supercapacitors has actually used lots of active materials inside of this device. But the problem is these active materials has to store the ion into these materials to enable the charge, to enable the charging. But the ions normally, when they contact the surface of the material, is okay, but they are really extremely hard to migrate into the material. So over 90% of these materials, even though they are there, being treated as a dead weight. And our strategy is creating pretty much like a candy cane structure between one active material with another polymer, which we use it as a pathway for the ions to actually migrate through these materials. So in this way, we actually maximize the use of the materials from maybe only 10% being used, we can jump it to 80% being used. And as a demonstration, we actually double the capacitance of the device and approaching the theoretical limits of these active materials, actually. And also the cycling stabilities as well as the mechanical robustness, the flexibilities has been demonstrated, has significantly enhanced as well. And this actually being carried out by the collaboration between, in material science, between the polymer scientists as well as the energy storage investigators. And well, what has been so far demonstrated is we actually collaborate with Cambridge Enterprise. We actually put our market sheet on the Cambridge Enterprise website. We want to commercialize these technologies. We also wrote a review about these active materials, discuss what's happening in the entire market as well as the research front end. Also, I was being invited to the American Chemical Society giving interviews, being interviewed about what's happening about this candy cane device. And part of the trip to New Orleans, actually early this year, has been funded by the CSAR Award. And currently, we're actually extending our working potential of this device. Previously, it's probably like half cells is around 0 watts to like 0.6 watts, and it's now been like using full cell, demonstrating from 0 watts to 2.7 watts. And we want to actually extend further, over the next couple of months. And also, we actually formulate our materials has been as an ink, where we can actually print on the substrate. And imagine that how people currently printing newspapers, we can probably later on print our device. That's how our dreaming is. And thank you for listening. Thanks a lot.